We are talking about estimation and confidence intervals. All right, so what are we talking about with that? So at the beginning of every chapter, don't we look at what we're talking about and try to break it down? Yeah? So estimation. What are we talking about with estimation? When we estimate something, what are we talking about? Huh? We're talking about guessing, aren't we? But are we just talking about throwing a dart at a dartboard? What are we talking about? Using what? It is using statistics, because statistics are characteristics of samples. So, big world of statistics, two realms, what are they?
Inferential and descriptive.
Very good, inferential, descriptive. Right now we're in what world? Inferential, aren't we? Okay, for this unit. So what are we doing? We're taking samples from populations. Those samples are intended to represent what's going on in that population. We don't have visibility to that population for some reason, right? Because it's too expensive to look at every member of that population, right? We don't have time to do it. It's impossible. And what's the best reason? We don't need to, because we got these statistical techniques that we can use. Okay, sampling techniques. All right, so estimation, we're talking about using the information that we do have about that sample in order to gain information about the population, aren't we? Okay, confidence intervals we'll look at in just a minute, but what is an interval? We've looked at what intervals are, haven't we? What are we talking about with an interval? We're talking about a range in there, aren't we? A range within a range of continuous data. Remember? Those continuous variables, remember? Okay. All right, so we'll look at the confidence bit in just a little bit, okay? All right, so we got a good idea what we're doing here. We're taking samples and we're making guesses about the population. Now we've already looked at one little thing about this, haven't we? We looked at the what? If this is our population, remember? And we took a sample from this population. Remember doing this in chapter 8? And the mean of that sample is right there. What was this area called right here between the x bar, which is the mean of the sample, right? And the mu, which is the mean of the population. What was that called? Who remembers?
Sampling error.
Very good. The sampling error. Very good. Really good. All right. So we've already looked at it a little bit, haven't we? But again, if we don't know what's going on with this population, then what do we have that's going to tell us anything about this data set? We got this sample that we pulled, don't we? All right? So, sometimes this is the best we have to go off of. All right, so in this case, what we just looked at, I'm going to redraw it here. But we don't know where that mean is, let's pretend like, okay, for the population. This x bar, this mean of the sample, is going to serve as a point estimate of the population, okay? So what a point estimate is a statistic of a sample that serves as the best estimate, the best guess we have as to the corresponding parameter of the population. So what I'm saying here is we got this mean of this sample, don't we? Again, we don't know what the mean of that population is, but we do have a point estimate. Our point estimate for that population is this mean for the sample. So we're saying, hey, we don't know what the mean of the population is, but we did do this sample, and we got a mean from there, and that's going to serve as our point estimate, our point estimate. Can we have a point estimate regarding deviation, standard deviation, or variance, or anything else? Yes, we can. It doesn't have to be of the mean, okay? The point estimate is just the statistic from the sample that we use to represent what we don't know, or is the best guess, putting a pin in it, right? The best guess that we have to represent data that we don't know about the population, okay? Now what would you do here though? Okay, so if you pulled this sample from this population, you know it's from this population somewhere, but you don't know any of the characteristics, any of the parameters of this green one, this population, okay? What would you do about this mean right here? Would you say, well, since I pulled this sample, and the sample mean was whatever this is at x bar, then that means my population mean is x bar. Or could you say it like this, maybe? Something that we do all the time, I think. You know, I do it all the time. I say, well, you know, I got this sample right here. So let's say this is a certain amount. This is dollars, okay? we'll look at an example of this in just a second. I can say, well, I'm pretty sure my X bars around my sample somewhere within that population, give or take a little bit, yeah? Within this range, huh? See what I'm saying? I give myself a little leeway, don't I? Okay? I hedge my bets a little bit. I know, I'm pretty sure my sample size is big enough to where I can say, hey, it's probably around there somewhere. I don't know where. What if I could say, I'm 90% sure that it's within this range? That being the population mean. That'd be pretty powerful, wouldn't it? Think you could use that in the business world? Absolutely. Let's look at this example real quick of a point estimate, okay? Suppose the Bureau of Tourism for Barbados wants to estimate the mean amount of money spent by tourists visiting the country. The island, right? A Caribbean nation, Barbados. Has anybody been to Barbados before? I've never been down there. I don't know if it's just an island or a bunch of islands, but anyway, it's a country. All right. So they want to estimate the mean amount of money spent by a tourist visiting. They randomly select 500 tourists. Is 500 tourists enough to tell you what you want to know? We don't know, do we? We don't know what the population of tourists is, do we? That's neither here nor there. We'll get to that. Selecting sample sizes later on, okay? How to select the appropriate sample size in this chapter. Okay, really important concept. We'll get to it later. All right, so they randomly select 500 tourists as they depart the island, and they ask about their spending while they were there. The mean amount spent by the sample of 500 tourists serves as an estimate of the unknown population parameter. I.e., it's a point estimate, isn't it? That's our X bar. Let's say these 500 tourists, you got an average of $2,000 that they spent on their vacation. Yeah, so what would our X bar be? $2,000. Okay? So what if you could say, well, I'm 95% sure that the tourists spent between, let's say $500 each way, $1,500 and $2,500, yeah? Be pretty powerful, wouldn't it? Okay? So that's what we're going to learn to do. And we would say we're 90%. We'll give a confidence to this interval, confidence interval, right? Okay, we'll say we're certain percentage sure that the mean of the entire population, all the visitors to Barbados, fell within this range right here of the X bar, of the average that we took. Okay? Of the sample that we took. Everybody understand where we're kind of going with this? Trying to be as clear as I can here. Okay. Okay, so confidence intervals. Confidence interval is a range of values within which the population parameter is expected to occur. Okay? So again, we got our dollars here, don't we? This $2,000 spent in Barbados, or on average, spent by the tourists that we sampled. Okay? The confidence interval would be 1,500 to 2,500 from sample data, right? This is likely to occur at a specified probability. That would be the confidence part of it, wouldn't it? At the 90%. I'm 95% sure that the mean of the population falls within this interval. Okay? And guess what? We do have a formula for that, don't we? Okay, so read what the slide says. What depends on, or what does the size of this confidence interval depend on? And whether the mean falls within it or not. Well, let's have a look. The variables I see are this one, the number of observations in the sample, the n. That makes sense, doesn't it? The larger your sample size, the what? The more what? Law of large numbers, huh? The more accurate to the population that it came from is going to be, right? To the true mean it's going to be. So if you have a big n sample size, what does that tell you? Well, it tells you can shrink this range, first of all. This range will shrink. Because if you have a huge sample size, you already know you're close to the population mean, don't you? Yeah? What about the second one? The variability of the population, usually estimated by the sample standard deviation. Okay, we're going to change this for right now to the population standard deviation, but just say standard deviation in general. So what are we talking about when we're talking about standard deviation? We're talking about the what? That's a measure of dispersion, right? Of spread. So we're talking about how different the data is. What I'm saying is if this underlying population or the sample, either one, if they're really skinny, what's going to happen? Well, if the population is really skinny, then you don't have to have this widespread in here for the mean to fall within, do you? Because it's not as wide. But what if you have a lot of varied information within your data set? Well, then you might have to spread this thing out to get an accurate representation of everything that's going on in that population. Right? We'll get to this in just a second. I think it'll make a little more sense when we do an example of how it all works together. All right, now, what's the third variable we're looking at? Blah, 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 blah. Oh, the desired level of confidence. That's another thing. How sure do we want to be? Do we want to be 95% sure that we capture the mean of the population within this range, the mu within this range? Or do we want to be 10% sure? If we want to be 10% sure, then we can just say, let's just say our population average is the same as our sample average. Were you sure about that? Well, I'm 10% sure, so why not? Right? Versus I'm 95% sure that, boom, it falls within here. I better be more accurate, right? So that thing better be a little bit wider, if I had to guess, to make sure we're going to capture that population mean within this range. That line falls within this range somewhere. Right? Okay. So like I said, there is a formula for that. Level of confidence, and I want you to check something out on this slide real quick. What does this say right here? We always look at these titles, don't we? Level of confidence, what does that say? That second phrase right there after the comma.
Standard deviation.
Very good. Standard deviation of what, though? It's Greek, right? Population. Population Greek. Right? Sample Latin. Remember that? We got to remember that, people, because that's a bigger deal now than ever, isn't it? Because we're going to be we've already been pulling data from samples and populations, haven't we? And using them in the same formula. So we got to know where our data's coming from. Is that camera still on?
Yep.
All right, I'm not going to get famous if it turns off now. All right. So, should I sing? That'll give me some hits, some likes, some hits. What is it on YouTube? Views, that's what it is. All right, level of confidence, standard deviation of the population known. Okay? Now that you got to really pay attention to that. Okay, and I'll show you why in just a minute. All right. To determine the confidence limits when the population standard deviation is known, we use the Z distribution formula. We've used that before, haven't we? That Z-score thing? What do we do with that Z-score? Where do we plug that into? We plug it into something, don't we? Oh, what? To find those areas? Where do we find those areas from the Z-scores? Who remembers? Don't we have a table for that in the book? All right, so guess what? We're going to be using the table again, but not yet. Let's look at what we're talking about here first. Here's the formula that we have to use when we do know the population standard deviation. And again, these are all the variables we just looked at in the last slide, aren't they? Remember the N right there and the S, it's actually sigma in this case, and the desired level of confidence. Okay, so let's look at this formula. Let's break it down real quick. X bar. What does X bar stand for? What is X bar? Huh?
Sample mean.
Very good. It's the sample mean, isn't it? Versus mu, which is the population mean. We're not talking about that. We're talking about sample mean. Okay, and we're not saying it equals something, are we? We're saying what? Plus something and minus something at the same time. Because we're talking about a range, aren't we? So we got a point estimate. Remember? The X bar, we got a point estimate. Here's our population, say. Ooh, that's ugly, but whatever. And here's our sample from that population. And remember that X bar is our point estimate. We don't know what the mean of this population is. We're trying to figure out a range where it might fall. But we do know what the mean of this sample is, don't we? And it's X bar. Right? So it's our point estimate. Best estimate we got. It's our best guess. Because it's all we got. All right, so X plus or minus. Now we want to put a range on this X bar, plus and minus, to see where the mean of this population falls. All right. Or to give space for that population mean to fall. Okay. Z, whoa, so that's what we're talking about with that Z. Okay, now where's that Z going to come into play? What does that Z score represent? Huh? It is the confidence. Very good. It's how sure we want to be. And how sure we want to be is going to be represented by the area under the normal probability distribution curve. Okay? But we'll get to that in just a second. All right? I'm going to show you how to figure it, and it'll all make sense. But I want to point one more thing out real quick. What are we multiplying that z by? What is this thing called right here? Sigma over the square root of n. What is that called? Told you to burn it into your brain.
Standard error.
Very good, the standard error, isn't it? Remember that? The standard error. Okay, so what we're talking about is this x bar plus or minus our confidence times the standard error to set it to itself. Yeah? So it makes sense, doesn't it? Okay? So let's do an example. Now, what's something I said we're going to do? Just mechanics of each of these problems we're going to do from now on. What are we going to do? We're going to draw out our graphs, and what else are we going to do with our variables? We're going to write them out, aren't we? Our variables, yeah? So in this formula, what are the variables that I have that I need to plug in here to solve for this confidence interval problem?
Sample.
Very good. Sample mean, x bar. What else?
Standard deviation.
Z. Very good. Standard deviation of the what?
Population.
Population. And what else? What's that last one? Yeah, the sample size. Very good. And with those four variables, which I'm going to tell you right now will be given to you in the problem more often, well, they have to be, don't they? You can solve the confidence intervals, okay? Now, let's do an example, and I think it'll make more sense. So, the American Management Association, okay, is studying the income of store managers in the retail industry. A random sample of 49 managers. What is that? A random sample of 49 managers. That looks like a variable to me. Where did that fall? In. Very good. That's our sample size, isn't it? 49 managers. Reveals a sample mean of $45,420. That looks like a variable. Where does that one fall?
X bar.
X bar. Very good. 45 what? 420, dude. And then the standard deviation of the population is what?
2050.
Where does that fall? Is that our z or is that our sigma? It's the standard deviation of what?
2050.
The population, right? 2050. So I want to point something out interesting right now at this point. So we don't know where the mean of the population is, do we? That's we're trying to find the range where the mean of the population probably falls, right? But we do know the standard deviation of the population is given to us. Does that strike you as odd? What I'm saying is it weird that we know the standard deviation of the population, but we don't know the mean of the population? Does that often occur in real life? What do we need in order to figure out the standard deviation? Huh?
The mean.
We need the mean to figure out the standard deviation, don't we? So how are we going to know the standard deviation of the population without knowing the mean of the population? I don't know, it's kind of weird. But it's given to us in the problem, so don't worry about it for this one, right? Okay. So, we're still missing a variable before we can solve this thing, aren't we? But we got 3 questions to answer. Let's just start working on them, see what happens. What is the population of the mean? What's the reasonable range of values for the population of the mean? And how do we interpret these results? All right, so the first one, what's the population of the... What does the population mean? That's what I meant to say. What does the population mean? What's the population average for this population? What did we just say? Do we know what it is? We don't know what it is, but we got to guess, don't we? What's our best guess?
2000.
Well, no, do you think... No, what's the best guess for the average salary for retail managers? The population, huh?
45,420.
45,420. And why is that our best guess? That's all we got, isn't it? We took the sample, and that was the average from the sample. So let's just draw it like this. We got this point estimate, and we're going to come up with a range that sucker probably falls within. That sucker being the mean of the entire population of retail managers. Okay, that point estimate is what? 45,420. Now, we want to figure out what this range is right here. What the range is, okay? Is ultimately what we want to find out. Into what confidence level? Well, let's answer question 2. What's the reasonable range of values for the population mean? So let's look at the answer right here. The AMA decides to use a 95% level of confidence. Oh, that's interesting. A 95% level of confidence. So we want to be 95% sure that whatever this range is right here, that the mean of the population of every retail manager, the average salary of every retail manager in the United States falls within this range somewhere. We want to be 95% sure that that happens. Okay? Why 95? Why are they using 95? Okay, 95 is the accepted practice, the accepted confidence for an experiment, okay, in the scientific world. 95 is going to be the number that we use for this class. We want to be 95% sure, okay? P-values on the flip side, 0.05, 5%. We'll get to that maybe next chapter, but maybe two, 3 chapters. I don't remember. But anyway, 95%, that's the number, okay? We want to be 95% sure, okay? Less than that, it's not scientific, okay? More than that, you're a little too strenuous, okay? All right, so we want to be 95% sure. Now, what did you say the Z represents? Yeah, it's going to be our confidence level, isn't it? So how are we going to turn this 95% into a Z value that we can use in this math, in this formula? How do we convert Z values? How have we been converting Z values? I'm going to tell you right now, we can't use a percentage. So we can go to our book, can't we? Huh? It's that chart. It's the table. Unfortunately for y'all, yes it is. So let's go to the ebook. Just kidding. Y'all should be used to it by now, right? Let's navigate to the last point where we were at. Let's see, page 756 is not this table. And it's not that Poisson distribution. It's this one. Areas under the normal curve, isn't it? Okay. So, here's what we want to find. We want to find not the 95% to the right or to the left. We want to find that middle 95% of this curve. Okay? Let me draw this a little bit nicer. First, let me draw this a little bit better. And then let's draw... Too many markers today. Okay. Boom. We're looking for the range, right? So, we want to find the middle 95% of this curve. Okay? So if I were going to find, this is the population. Okay? This is the population of all managers. Boom. Now, if I were, what percentage of the area under the curve is this from here over?
50.
It's 50. What about from here over?
50.
Very good. So if I wanted to find the middle 95%, what would I do?
47.5% on each side.
Very good. How did you get that?
Divided 95 by 2.
Divided 95 by 2, and you get 47.5% on each side. Now remember, why do we know we have to do it at one side at a time? Because remember how high our table goes. To 49.90, remember? The 3 standard deviations, yeah? It goes to 50% to the max, isn't it? This only does one side at a time. So if we're taking that middle chunk out of this area, and we want it to be symmetrical on both sides, then we have 47.5%, don't we? This is 47.5%. This is 47.5%. This is how much? It's 2.5%, isn't it? And this is 2.5%. So what's 2.5% plus 47.5%? Huh? 50%, isn't it? So we got 50 and 50. Everybody see that? So we want to find 47.5% on our table. How are we going to do that? We look at the table and do what? We count up. We find it. We literally go in there and find 0.4750, don't we? And where's that going to be? Well, here's 4608, 4686, and it's still going up. It goes up, doesn't it? And whoa, what did I just stumble upon? What does that say? Right there. 47.5%. Does everybody see that? Everybody good? All right, so what would our corresponding z-score be for that 47.5%?
1.96.
Very good. 1.9. Where'd you get that?
The left hand side.
Take that 1.9 to the left, and then we go up, don't we? To 6. And we have 1.96. Oh, yeah, 1.96, don't we? So, what is my corresponding z-value? 1.96, isn't it? And now what do I have? And why is it 1.96? Because we wanted to be, we're 95% sure, aren't we? Our confidence level is 95%. And how did we get that? The area under the curve for that 95%? We divide it in 2. And then we draw it out, don't we? To make sure we're getting the right number. Now that being said, what number did I say we're just about always, though not always, but just about always going to use in this class for our confidence level? 95%. So what is our z just about always going to be whenever it's 95%? Every time. You don't have to keep looking it up. It's always 1.96. Unless it's 90, and then you find what? 45% of the area under the curve, don't you? Because you split the 90 in two, find 45 and back it out. And 99 is the other big one. So 90, 99, but most of the time is 95, okay? So it's always 1.96. In fact, that 95% is so prevalent, let's look at the sample, the example that they have up here. What is it using? A z-score of what? 1.96, isn't it? To show you how to use this table. That's how prevalent it is. 1.96 is the example they use. So even if you forget, just look at the chart here, and you got your 1.96, okay? Now, what did we used to say when we were kind of explaining what the empirical rule was? 95% of your data falls within how many standard deviations? 2, remember? Well, technically it's 1.96. We just say 2 to make it clean. Use nice big round numbers, don't we? Technically, it's not 2 standard deviations. It's 1.96, isn't it? Okay? But whatever. So that's another way to remember. Remember, it's close to 2, right? But not quite at 2. Okay? For 95% of the area under the curve. Yeah, 95%. Boom to boom is 95%. Right? Okay. But regardless of all that, we got everything we need now, don't we? To plug and play. All right? So, this is what these things look like. I'm going to draw this over here and get it out of the way. This is what these things look like. We got our point estimate, and we got our range, don't we? And our point estimate is this 45,420. Isn't it? Now we got to find this range. How are we going to find this range? This answer is going to give it to us. So let's fill in the numbers here. X bar is what? 45,420 plus and minus. Our z-score is what? What is the z? Very good. 1.96 times the standard error, which is going to be 2050 over what? Square root of 49. And hopefully the math is done for us. And it is. So we have 45,420 plus and minus $574, isn't it? This formula is a little different. It's not this isn't x equals, is it? It's x plus and minus, okay? So, we have our point estimate down here, and now we're going to take this plus $574 and minus $574. Which is what? 45 what? No, it'll be 46 something, won't it? No, it's right there. 40 what? 5,994. On that end of the range. And what's on the low end of the range?
44,846.
There we go, 44,846. So now, what can we say about this confidence interval and the underlying population? We are what percent sure? We're 95% sure that what's going to happen? The what of the population?
The mean,
Mean of the population is going to fall between what?
those two numbers.
$44,846 and $45,994. Pretty powerful, is it not? So again, we could not take the one sample and say, yeah, we think the mean of the entire population of members of the American Management Association, the retail managers, is 45,420. But we can say we're 95% sure that the mean of all those managers, the whole population, the mean of their salaries, falls between 44,846 and 45,994. Within that range of what? $1,148, yeah? So we found an $1,148, is that right? Yeah, $1,714, yeah, $1,148 range where we're sure that we're 95% sure that the average salary of all the managers, not just the sample we took of the whole population, falls. Okay? Is everybody with me? Pretty powerful stuff. Do you think that could be useful? Absolutely. You're actually learning stuff you can use in this class. Wow, refreshing, huh? All right. So, that's all well and good, right? But what did I say is kind of weird about this problem here?
We know standard deviation of the population, but not the mean.
Yeah, it's kind of weird, isn't it? Because we got to have the standard deviation, we got to have the mean of the population to figure the standard deviation. So unless somebody's already figured something like that up and given you that standard deviation or gone a really backwards way to do it, then that's not really that useful, is it? And why would they hold back the standard deviation, the mean, if they're figured? It just doesn't make sense, does it? So what's the alternate scenario?
The mean is given, but the standard deviation isn't.
That would be the alternate scenario, but what would be another scenario? Let me put it that way. Another scenario would be where you don't have the standard deviation of the population, right? If that were the case, knowing what we know about point estimates, what would we use to guess about the standard deviation of the population? The what? Standard deviation of the mean. Because we got that, don't we? We took the sample, sorry. We took the sample, didn't we? So we can figure the mean, we can figure the standard deviation, we can figure all that. So just like with the mean, we don't know what the exact mean of that population is, do we? But we got this point estimate. Well, a point estimate can apply to spreads too, can't it? That point estimate can apply to the standard deviation as well, can't it? Okay? And so what can we use? We'll just substitute in the standard deviation of the sample for the standard deviation of the population. That easy. Okay? So let's look at our formula right here. And what would we have to change? Well, I'm going to get rid of all these numbers here. Yeah? I'm going to get rid of the specifics of this problem. I'm going to leave that because we're going to be using this all the time, aren't we? This right here. And we're going to be using that too, although the numbers are going to change, but it's still going to be a point estimate with a spread. Okay, so what are we going to do here? We just said that we don't have this sigma, do we? All right? So we're going to use the point estimate from the sample, which is going to be a what? S, isn't it? Okay? Now, because we don't have the sigma, we only have the S, we can't use this z-score. Can you believe that? what are we going to do? We're screwed, right? No. Guess what we have? A new formula that has a corresponding what? Table in the book that you get to use. Okay. So, instead, when we have the S right here, we can't use the Z. Instead, we're going to use a T. Does everybody see that? We're going to use the t-test. The good news is it's a lot easier to use than the Z-table, believe it or not. But what's going to happen right here in our formula? Well, all we're going to do is replace the sigma with its statistical equivalent, and we're going to replace the Z with that T. And other than that, it's the same. All right? So not bad. But what is the difference here? How are you going to know whether to use the S or the sigma when you have a problem to do?
Whether we know the standard deviation or not.
Yeah, so whether it's given to you or not. If you're given the sigma, you got to be able to read the problem and understand what it's asking you. If it gives you the population standard deviation, then you use that z-score one we just did. If it gives you the sample standard deviation, then we're going to use this one. All right? Easy as that. Not bad, huh? Oh, actually, we're going to use the 95, but we're not going to use this again, are we? Because we're not doing, this is our z distribution, isn't it? We're going to be using the t distribution. So we still want to be 95% confident most of the time, but we got a different distribution to use, okay? We're going to come up with a different number in there. So let's do an example of this real quick. I think that's the best way to do it. And there's one in the book here. And here it is. Okay. So, a tire manufacturer wishes to investigate the tread life of its tires. A sample of, I'm going to read the whole thing first and then we'll plug in the variables, all right? A sample of 10 tires, they took a sample, 10 tires, put them on a car, drove them, 50,000 miles, revealed a sample mean of 0.32 inches of tread remaining with a standard deviation of 0.09 inches. So what are we talking about? We're talking about the tread. Does everybody understand what we're talking about here? The tread on a tire? How you stick a quarter in the grooves in the tire to measure the tread? Yeah? Okay, we're talking about the tread of the tire. Constructed 95% confidence interval for the population mean. And the question we want to answer is, so 95%, yeah? The question we want to answer is, would it be responsible or reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount of tread remaining is 0.3 inches? Boy, that's a mouthful, isn't it? So we're going to have to break it down one step at a time, aren't we? How do we do that? By drawing it out and writing out our variables. All right? So let's reread this problem. Stay calm and reread the problem. A tire manufacturer wishes to investigate the tread life of its tires. Okay, whatever. A sample of 10 tires. Uh-oh, that looks like a number we can use. Where does that go? N. That's our sample size, isn't it? Driven 50,000 miles. Where does that go? Where does 50,000 go? Huh? It goes nowhere, does it? Why is that? Huh?
It's just extra information.
It is, isn't it? It's extra information put there to throw you off. All right? So I told you, I warned you about this, didn't I? The deeper we go into the book, the more they start throwing stuff in like that to try to throw you off. Okay? They'll put in weird model numbers that look like numbers. They put in stuff like this. All right? So be conscious of that. Don't let it sway you. You know what you need to pick out of here because you have it written down. And it tells you in plain English what it is. Just stay calm and pick it out. All right? Blah, blah. Revealed a sample mean of 0.32 inches. What is that?
X bar.
X bar, very good. 0.32. With a standard deviation of 0.09 inches. Now, is that the population mean or is that the sample mean?
Sample.
It's the sample mean, isn't it? That's why we're going to use the T and the S in here. We already knew we were going to because it's a sample problem for this lesson. But you got to be able to read it and say, wait a minute, is that the sample mean or is that the, standard deviation or is that the population standard deviation? Okay, so the sample standard deviation is 0.09. That's an S, not a sigma, right? 0.09. Whoa, it looks like we're getting a whole bunch of numbers we can plug in here, don't we? So we're going to construct a 95% confidence interval for this population mean. What's the population mean? We don't know it, do we? That's the whole point. But we're trying to find a range where we're 95% confident that it falls within that range. Okay? Now, after we do that, we want to know whether it is reasonable to conclude that after we drive it, that 50,000 miles, population, the mean for the population, all the tires, the mean amount of tread remaining is 0.3 inch. I.e., are we 95% sure we can include it on our advertising material? That it's going to last, at 50,000 miles, you're going to have 0.3 inches of tread remaining. Okay? So, we have a point estimate here, don't we? In our graph, in our drawing here. And what is that point estimate?
Sample mean.
It is the sample mean, isn't it? 0.32. Right? Now we want to find this range here, don't we? And we want to see if 0.3 falls within this range. Alright? So let's give it a look. Now there's one thing more that we need to figure out before we can solve this thing. And what is that? What variable do we not have? T. So how are we going to find that T? Alright. I want everybody to open their book. Connect book, that is. McGraw-Hill, the publisher. 17th edition. Copyright, 2018. Sorry, I'm just giving them a plug for my video. No, I'm just kidding. Alright. And let's go back to the tables. What was it? B2, whatever? At the end, the appendix. And we're going to find that areas under the normal curve, but we're not using that one this time. We're going to scroll down from there, okay? We're going to scroll down. Here's a table of random numbers, but after that one, remember using that in our samples, simple random sampling, on page 763, but we're not using that. We're going to go to page 764 to students' T distribution. All right, why is it called students' T distribution? Is this just for students? And if you use a different one when you're in the working world? No, it's the guy's name, okay? So don't let that throw you off. The T distribution, students' T, all the same thing, okay? It's an interesting story, actually. The pseudonym of this guy, I can't remember his name, who came up with this, but he came up with this, he figured this out because he was trying to measure ingredients to go into Guinness beer. He worked at the Guinness Brewery back in the 1700s in Dublin, Ireland. And he came up with this statistical method because, I can't remember which of these, there's several things you can do with this, but I can't remember what exactly he was trying to do. But back then the bosses didn't want their subordinates, their employees publishing stuff like this. Okay, they didn't want them looking like crackpots. So he wrote under a pseudonym called Student, okay? So that's why it's Student's T. Don't let that confuse you. For some reason that did confuse me before, but anyway. Alright, so how are we going to use this sucker? Like I said, believe it or not, it's easier than the Z-table. But there is a catch. Alright, you can do several things with this, and we're going to be using every usage of this table, okay? But for now, we're in confidence intervals, aren't we? So we're going to ignore these 4 rows right here for now. Okay? Just block them out, pretend like they don't exist. All we're using right now is confidence intervals. And which confidence interval are we using? 95. Boom. That's the most popular. Again, sometimes it's here and sometimes it's here. Rarely here. But this is the big one. Okay? Now let me ask you something. We got to find, it's a table, right? So we're going to have to find the cell. We're going to have to find where the column and the row meet somewhere. But what is this DF thing? Okay. DF stands for degrees of freedom. Okay? Now degrees of freedom is calculated by taking the sample size and subtracting 1. It's n minus 1. Have we seen n minus 1 somewhere before? Who remembers n minus 1? Where have we used that? Do you remember it? Do you remember when we were doing those standard deviation problems before and we were using the sample? Remember, and we put it over n minus 1 instead of just n? Okay. Well, obviously you don't remember that. But anyway, when do we use n plus 1 for degrees of freedom? Never. When do we use n times 100? Never. When do we use n minus 2? Never. What is degrees of freedom? N minus 1. Okay? Because guess what? If we have 10 variables right here, and they have to add up to something, 9 of those can be whatever they want. But what does the 10th one have to be? Whatever the difference is, isn't it? It's not free to be whatever it wants. Alright? So just think, the last one, poor number 10 right here, out of the 10, has to make up the difference for the rest of them. But the first 9 can be whatever they want, can't they? Okay? Don't worry about that. Just say this. Degrees of freedom equals what?
N minus 1.
Which is going to be what right here?
2.262.
What? No, degrees of freedom, not the T. But what?
9.
How many? 9. Very good. All right, so we actually have an extra variable in there, don't we? But what were you talking about right there? What were you talking about?
That's corresponding number on the chart.
How'd you find that?
So I found 9,
9 degrees of freedom at where?
95%.
At 95% confidence, okay? So what we're going to do is go over here to 95% confidence level. Everybody see that? And we're going to take it down to the number of degrees of freedom. How many degrees of freedom do we have right here? In this problem? 9. So let's go over to 95. And what's the answer right here? 2.262. Does everybody see that? Pretty easy to use, isn't it? It's easier than the z-table, isn't it? Okay? So now we've solved for our t. 2.262. Now should you remember 2.262 since we're always at 95? Why not?
Because your degree of freedom is going to change depending on the sample size.
Because our degrees of freedom are going to change, aren't they? It depends. We're not going to have the same. The z doesn't depend on the sample size, does it? This does. Okay, and that's always going to be changing, isn't it? So these aren't. You don't need to memorize the 95% on this one. Okay? But now what can we do? We got everything we need, don't we, to solve? So let's go ahead and do that. So what's our x bar? 0.32 plus n minus what? 2.262 times what? 0.09 over the square root of what? 9 or 10? 10. It says n, doesn't it? It doesn't say degrees of freedom. Okay. And again, is this math done for us, or do we need to do it? It's done for us.
What page is that on, that example?
The table, you mean?
No, the example you're reading.
It's on slides.
Okay, it's not in the book.
It might be. I don't know.
I couldn't find it.
Okay. In 911, section 911. Okay? All right, so what are we talking about here to solve? 0.32 plus and minus what? To do that. 0.064. So, looking down here at our graph, what are we talking about? 0.32 plus 0.064 and 0.32 minus 0.064, which is going to be what? 0.384 and 0.258, 56? What is it? 256. Does everybody see this? What's up?
So how did you get the degrees of freedom again? Sorry, I missed that.
So degrees of freedom, every time, all it is n minus 1. What's n here?
Oh, 10.
N minus 1 is what?
9.
That's all it is. Sample size minus 1. Every single time. Okay? And it's all, we're just being conservative. That's all it's doing, okay? But you will get the wrong answer, though, if you use the sample size, okay? All right. So what are we saying here? We're 95% sure that what?
Falls between those.
What does? What's the real question here? Would it be reasonable for what? For the manufacturer to conclude that after 50,000 miles, the population mean amount of tread is 0.3 inch. So it's a little different the way it's phrased, isn't it? We're looking at it in a different way. We don't know what the population mean is, but we're asking, is it reasonable to conclude that it might be X, whatever that is, yeah? And what are we asking? Might it be reasonable to conclude what? 0.3, right? Where does 0.3 fall in this range? Does it fall in this range or outside of this range? Falls inside. Where does it fall? 0.256, 0.32, so it's about right here somewhere, yeah? Point, what? 30, right? 0.30. So is it reasonable to conclude that we could say in our marketing material, after 50,000 miles, the population mean amount of tread is 0.3 inches? 95% sure, yeah. Pretty cool, right? Can we use that in the real world? Absolutely, you better believe it. Who's thrilled? Hey, it's not Monday. Okay, well that's all I have for today. Does anybody have any questions? Well, let's do a quick little review here. What time are we looking at? Any time to go? What are you talking about, man? We've got plenty of time. All right, so what are we talking about today?
Yes, please.
The point estimate, which is what? It's a sample statistic that estimates, that represents the best guess we have about what? Very good, a population parameter that we don't know about. We don't know what the population is. That's why we took the sample, right? And from that sample, we're doing the best we can to judge what's going on in the population. Okay? So chances are that mean we took from that population isn't right on, is it? But we can say, I'm 95% sure that that population, give or take a certain amount, that the mean of that population will fall in that range, right? So we're hedging our bets, aren't we? We're kind of expanding that mean, aren't we? To include a little bit more, so that we can capture the mean of the population. Make sense? And so there's two different scenarios. Sometimes we'll know that standard deviation of the population. In that case, we use the what value? The z value. Very good. And we back it up from the table, don't we? And if we don't know that population standard deviation, what do we have to substitute in there? Another point estimate, right? That point estimate being what? Standard deviation of what? The sample. If we don't know about the population, we just use the one from the sample that we do know. Okay? And we use what test instead of the, what value instead of the z value? The what? Huh? The t value. Very good. Other than that, it's the same formula, isn't it? Degrees of freedom is what? How do we find that, Peyton?
N minus one.
N minus 1, there we go. And that's your degrees of freedom. And you plug it on